Hello everyone, welcome back to Must Electronics. This file right here, this is the end result of everything we have done in this series so far. Episode 3, setting up the build environment. Episode 4, downloading 250 GB of source code. Episode 5, understanding what is in that source tree. Episode 6, understanding how the build system works. All of that to produce this one file, a bootable Android 14 image, built from source for the Raspberry Pi 4. In this episode, we actually make it. We run the build live, we watch it compile, and at the end, we walk through every output file and understand exactly what it contains and why it exists. Commands are in the description below. Let's build Android. Before we run anything, let me show you where we are starting from. We are starting with a clean out directory. No previous build artifacts. Everything will be compiled fresh. If you already have a previous build and want to follow along, you can clean it with make clean. Currently I have a previous build. Let me clean it with make clean. Yeah, the make clean is completed. Let me verify if the out directory is deleted or not. Still we could see out directory, but let's see if there is any content inside the out directory. Okay, it's just a zoom matrix and everything else is deleted. So we can start the build freshly. If you have any doubt, you can delete the out directory. Yeah, now the out directory is deleted. This is the most honest way to show you the build from zero. No shortcuts, no cache results. Just source code going in and a bootable image coming out. Three commands build Android. Let me run them one at a time so you can see exactly what each one does. The first one loads the Android build environment into the shell. Notice something interesting. No output, nothing at all. Just the prompt returning immediately. That is correct. envsetup is not supposed to print anything. It silently loads a set of helper functions into your current shell session. That is lunch, mmm, croot, godir. These functions only exist inside this shell session. Open a new terminal and they are gone. You have to source env setup again. To prove something actually happened, let me show you. Type lunch. See that lunch is a shell function, not a program on disk. Before env setup, this command would say lunch command not found. Now it exists, loaded silently into the shell by that one dot command. That is why the dot before build envsetup.sh matters. It runs the script in the current shell, not a subshell. If you ran it as bash build envsetup.sh, it would load it into a subshell and disappear the moment that subshell exits. Second command, lunch. This is where you tell the build system exactly what you are building and for what device. Look at what lunch prints inside those two lines of equal signs. Platform version 14. This is Android 14, not AOSP trunk, not a preview, the released Android 14. Build ID AP2A 240905.003. This is the exact Android 14 release we synced. The AP2A you passed to lunch is derived from this build ID. Target product AOSP RPI4. This tells the build system to use product definition from device BRCM RPI4 AOSP underscore RPI4.mk file. Every board specific flag, every device specific package loaded from there. Target build variant user debug, not user. That would disable root access and ADB, not ENG. That would include too many debug tools. User debug is the developer's sweet spot. Full debug capability, close to real product build. Target ARC ARM64. The Raspberry Pi 4 uses a 64-bit ARM processor, Cortex A72. Primary binaries will be ARM64. Target second ARC ARM. This is something most people miss. The build also compiles 32-bit ARM binaries. Android still ships some 32-bit libraries for compatibility reasons. So this build actually produces both ARM64 and ARM binaries in parallel. Out dir, out. All output goes into the out directory at the root of the source tree. Android itself is telling you if you want faster local builds, use ENG instead of user debug. For day-to-day development, that is worth knowing. But for a build you want to test and benchmark on real hardware, user debug is the right choice. After running launch command, every build command in this session knows all of these settings. You do not have to pass any flags to make. Launch set it all up. This is the one you have been waiting for. Notice, we are not running just make by itself. We are asking for three specific targets: boot image, system image, and vendor image. Make by itself would build everything, including host tools, test binaries, and a lot of things we do not need for this device. Specifying the three image targets keeps the build focused and significantly faster than a full build. -j $n proc tells make to use all available CPU cores. The shell expands nproc to the number of logical processors on this machine. On a 12 core machine, it is -j12. Now watch what happens. The first thing you see is Soong running. It is reading every android.bp file in the source tree and generating the Ninja build plan. This takes few minutes depending on your machine. Watch for the moment it hands off to Ninja. There it is. Those bracketed percentage lines, that is Ninja. Soong is done planning, Ninja is now executing. Thousands of compilation jobs running in parallel across every CPU core. Every line scrolling past is a real piece of Android being compiled. C++ source files in system core directory being turned into native binaries. Java classes in frameworks base directory being compiled into DEX bytecode. Resources in packages apps settings directory being processed by AAPT2. Native libraries for the Raspberry Pi's ARM64 processor being linked. Hour after hour work, all directed by the dependency graph that Zoom calculated before a single file was compiled. Finally, build completed successfully. Last time it took around 5 hours 30 minutes, but this time it took 7 hours 25 minutes. It all depends on the RAM and the number of cores in the system. The make command produces three separate image files, but to flash to the Raspberry Pi, we need them packaged into a single image that goes onto an SD card. That is what this script does. RPI for envsetup.sh is specific to the Raspberry Pi AOSP build. It comes from the device BRCM RPI for device tree. It checks for exactly three images: boot.img, system.img, and vendor.img. This creates a 15 GB disk image, partitions it, and copies each image into its own partition using DD. A fourth partition is created for user data and formatted as ext4. That is it. Four partitions, one file, ready to write to an SD card. Let me show you what we just built. Everything the build produced is in one place. Look at those files and look at the sizes. 5 files, but only 4 of them matter for flashing. Let me explain each one. boot.img 128 MB. This is the first thing the Raspberry Pi loads after the bootloader. It contains two things packed together: the Linux kernel and the RAM disk. The RAM disk is a tiny file system that loads into memory at the boot time before any partition is mounted. It contains in it the very first user space process on Android. First stage init mounts the system and vendor partitions, then hands off to second stage init, which starts all Android services. Now you will notice there is also a separate ramdisk.img file in that listing. That is a build intermediate. The build system created it first, then bundled it inside boot.img. The separate file is just a leftover artifact. It is not flashed separately. boot.img already contains it. Without boot.img, nothing starts. The kernel never runs. Android never starts. System.img. This is Android, the real Android. The entire framework, Activity Manager Service, Package Manager Service, Video Manager Service, all of that lives in system.img. The Java runtime, the native libraries, the system applications like settings, system UI, the phone app, all in system.img. On the device, system.img is mounted at system directory. When you run adb shell ls system, everything you see came from this image. Currently, I am not running this command as I have not connected Raspberry Pi to the system. Vendor.img. This is the Raspberry Pi specific layer. Everything that makes this build work specifically on Raspberry Pi 4 rather than any other Android device lives in vendor.img. The hardware abstraction layers, the GPU hardwares, the Wi-Fi firmware, the device-specific init scripts, the board config settings. Vendor.img is mounted at vendor directory on the device. This is the layer that bridges Android to the hardware underneath it. And this Raspberry Pi Vanilla AOSP 14 IMG file, 15 GB. This is what RPI4 mkimg.sh assembled from the three images. Four partitions, boot, system, vendor, and a fresh user data partition all in one file. This is the file you write to an SD card. This is the file that goes into a Raspberry Pi 4. This is the file that boots Android 14. The image files tell you what exists. Let me show you what is actually inside. This is the unpacked contents of system.img. The build kept an unpacked copy in out directory so you can inspect it. See framework directory. That is where the framework jar files live. Framework.jar contains the core Android API classes. lib64 directory, 64-bit native libraries. lib android runtime.so is in there. The library that bridges the Java framework to the native layer. App and private app directory. The system applications like settings, system UI, contacts, phone, installed as part of system.img. And this is the unpacked vendor partition. See lib64 HW directory. This is where the hardware abstraction layer implementation lives. audio.primary.rpi4.so for the audio hall. The GPU driver libraries for the video core GPU on the Pi. This is the layer we will dig into in detail when we reach the HAL episode. For now, the key point is this. Everything in vendor directory is device specific. If you are building for a Qualcomm phone instead of a Raspberry Pi, virtually all of vendor directory would be different, but system directory would be nearly identical. That separation is intentional. It is the whole point of the vendor partition. We just built Android 14 from source. Three commands and you have a bootable Android image. Let me put what we did into one sentence. We took 800 plus repositories of source code, fed it through Zoom and Ninja, and produced an operating system that runs on real hardware. That is not nothing. Most people who use Android every day have no idea this process exists. You now know exactly how it works. And right now, these images are sitting in a folder on a Linux machine. A file on disk is not same as Android running on hardware. Episode 8 is where that changes. We take the Raspberry Vanilla AOSP 14 image, write it to an SD card, slot that SD card into a Raspberry Pi 4, power it on, and watch Android 14 boot. The boot animation, the launcher, a full Android system running on hardware, built entirely from source code that we downloaded and compiled ourselves. That is next. If this episode helped you understand what actually happens when Android is built, please like and subscribe to Must Electronics.